Everyone. My name is Lepoutre. I'm a professor at the ESSEC Business School, and I'm delighted to be here with you and share this session. We have 4 very interesting presentations scheduled. For each of you presenters, that means 20 minutes of presentation and some time, or maximum, and some time for questions and answers. I see that we are still joined by other people, which is great. I think it's the great advantage of having this session occurring. So the first paper that we will be discussing is a presentation by Francisco Santos and Isabel Nicolai on a paper called Business Model Innovation in the EV Ecosystem. So Francisco, I propose you take the floor, and so I'll be your timekeeper. If you hit 17 minutes, I'll just give you a short mention. In 19 minutes, I'll do it again, and then I'll stop you at 20 minutes so that we have sufficient time for Q&A. Okay, floor is yours.
Okay, hello everybody. Can you hear me well? Because I'm having a bit of trouble with my connection.
No, we can hear you well, Francisco.
Oh no.
We can hear you well, but now the screen is frozen.
Yeah,
it's okay.
I'm having trouble with my connection right now. Can you hear me now?
Yes, we can.
Better. Okay, so let's hope that it works well. I will start sharing my screen.
Okay, so it seems to me that Francisco has disappeared. Just so in the interest of time, I am then proposing maybe it's better if we then switch to the second presentation. Otherwise, unless people want to join us later on, I'm not sure how to best deal with this. Let's see, hopefully he's reconnecting soon. I'm a little bit annoyed because I don't know if we start with the second presentation, maybe there would be people that wanted to join us at that time slot, which is sad for those people that wanted to do so. So, Tatiana, would you feel okay presenting already now and switching order, or is it?
Sure, it's okay. It's fine
yeah?
by me. Yes.
Okay. So then I propose that we do it this way, then we don't waste any time of anyone. So Tatiana, you'll be presenting a paper. I'm not going to take you present it yourself, that way we can move forward. Floor is yours, Tatiana.
Okay, thank you very much. So let's share the screen. Hopefully it will be fine. Okay, so I guess everyone can see my screen. I'll put on presentation mode.
Yeah.
And here we are. Okay, so what I will present today, so first of all, good morning. My name is Tatiana. I am a PhD candidate at the Sustainable Energy Systems program at Instituto Superior Técnico, which is the engineering school at the University of Lisbon. So what I will present today, so I submitted this work last year for the Paris conference, and of course the history catch up with us. And so I'm presenting today, it's the literature review for my PhD thesis. So it's the contribution of new mobility technologies and services to climate change mitigation and economic welfare. So as I said, this is the literature review that I finished at the beginning of 2020, and it's the first part of my PhD thesis. So first I'll give you a brief, I'll show you, hold on, goes here. Okay, so first a brief outline of the presentation today. First, I'm going to explain how this idea came about, what are the motivation and the background and the objective of this work today. And then I will present some results and also the conclusion and the next steps, because as I said, this was the first part of what is going to be my PhD thesis. And then I want to give you an overview of how this is going to match with what I'm intending to do for my PhD thesis that I'm supposed to finish next year. Okay, so the first part, motivation, background, and objective. So the big motivation for me was climate change, like what we are all living today, because a little bit about myself. I am an economist and I have a master's in public administration. And I started to work with energy policy right after the Paris Agreement came to exist. So it came to exist in the end of 2015, as we all know, and countries signed and ratified in the years following 2015. And the thing is that I started working with energy policy, and I started to work with climate change mitigation. And that was a big motivation for me, because I come from a country, Brazil, that we are already experiencing several severe impacts of climate change, like desertification and droughts. At this moment in Brazil, we are seeing a crisis in energy production, because the country relies a lot in hydropower production. And at the same time, we have around the world other climate change impacts. Last year was one of the worst seasons for hurricanes in the North Atlantic region. So, and we are seeing wildfires that they are starting even earlier in the year, much earlier than what they are supposed to start during the fire season. So we are seeing several impacts that they are getting worse. And the thing is that we have been paying attention to this for a very long time. And so the Paris Agreement came to be in the end of 2015. And in the agreement, it said that we are going to make the best we can to keep global warming until the end of the century, to keep it at 2 degrees, but making efforts to keep global warming to well below 2 degrees, around 1.5 if possible. And then policymakers, they ask, okay, so what do you mean about well below 2 degrees? And then in the end of 2018, the IPCC released a report, which came to be known as the 1.5 degree report, that says that, okay, so this is what it means. It's here on this slide. So pretty much we have this decade, 2020 to 2030, to reach peak emissions. And after that, we have to start mitigating emissions, and the best we can with technological advances in energy production, consumption, and so forth. And so that we get to net zero by 2050, and we may need to remove CO2 from the atmosphere. And in the best case scenario, we may stay under the 2 degree threshold, maybe 1.5, but then there's going to be some overshoot that, and pretty much bottom line is that we need to act right now if we want to mitigate the worst impacts of climate change until the end of the century. So this was a big motivation for me. So what can we do? What about, what can we propose? What are the options we have to mitigate these impacts? And then I look to transportation, because transportation is a difficult sector to decarbonize, because it relies very much on technologies that they use fossil fuels. So for the past 100 or so years in transportation, what we have used is the internal combustion engine or diesel engines that they are inefficient and they consume fossil fuels. So we haven't seen until very recently a technology improvement and advance so that we have engines that use cleaner fuels. Until very recently, we have had the electrical engine for many years, but it's gaining traction now in the past 10 years or so. So we have this sector, it's very difficult to decarbonize. It relies a lot on fossil fuels. It relies a lot in just one type of technology that use fossil fuels. So what can we do to decarbonize this sector? So we have a few options at hand. So renewable fuels, electricity, if it comes from renewable electricity generation, it is a renewable fuel, or hydrogen, or biofuels that they are harvested from sustainable sources, of course. So these are ways that we can decarbonize the supply of technologies that people use to consume transportation. As I said, electricity, it's another alternative fuel, and it's perfect as well because electric vehicles, they are much more efficient than the internal combustion engine. So electric vehicles, depending on the conditions of driving, it can get to 90% or more of efficiency. That meaning that the energy that fuels the energy that you put into the car, it becomes mechanical energy to move your car. Whereas the internal combustion engine, that number lies between 15 and 20%. So it's a lot of energy wasted. But also, so these are options from the supply side, the fuels and the engines that power your car. But at the same time, we can move to more sustainable mobility. The consumer may choose to use mobility in a more sustainable way, to use more public transportation or active modes like walking or biking. So there are solutions also from the demand side. And they are very much aligned to behavioral changes. So people, they need to change, they need to actively change the way that they consume transportation to become more sustainable. So these behavioral changes, these actions from the demand side to induce change in transportation consumption, they are going to be very important. So at the same time that we need to have more efficient engines like the electric engine and alternative fuels that they do not emit greenhouse gases, we also need to, it would be ideal that behavioral changes, they go hand in hand with all the innovation that is going on the supply side of transportation. So these innovations, people, they can start shifting from car ownership to service consumption. So instead of owning a car and driving it just 5% of the time, like cars, they are parked mostly around 90-95% of the time. So instead of having a car parked in your garage that it's going to be just sitting there most of the time, you can shift your consumption to service consumption. So anytime you need a car, you go to a car sharing station, or you call for an Uber, preferably an Uber that is shared with other people, so that it's even more sustainable. Because it is very important that a way to move to more sustainable transportation is exactly matching capacity to use. So instead of having one car riding around with just one person, and it has capacity to carry around 5 people, so why not increase this the capacity that's being used within vehicles? That would be a way to increase the sustainability of transportation consumption. And then the technologies and services that promote this more sustainable transportation consumption, that increase the capacity within vehicles, those would be share modes of transportation. Besides public transportation, of course, that has the biggest capacity of all the modes of passenger transportation. So those would be car sharing and ride hailing, and autonomous vehicles. But the thing is that how are these technologies being used? What do we know so far about them? What do we know about how they affect energy consumption and car ownership and greenhouse gases and gases emissions? So how do we know so far what the literature tells us that we have seen in the past 10 or 15 years that these technologies have been available? Not in the case of autonomous vehicles, it is in the theoretical phase of studying the impacts. But what do we know about how these technologies, they're going to have this impact? Can they help on climate change mitigation in passenger road transportation? And then that's the objective of this work so far, is analyze the current literature about these new mobility technologies and services to see how they are going to affect car ownership and how they interact with other types of transportation consumption, public transportation, and other modes of transport as well, and how are they going to impact energy use, emissions, and also the overall economic welfare of the population. Because when we talk about options to decarbonize transportation from the demand side, we are talking about the way people make consumption decisions about consumption. And people, they choose to consume one type of transport instead of other because by review preference, that's better for them. So if we are talking about people choosing things, then we also need to understand why they're choosing these things and what are the implications in terms of economic welfare that that choice will bring to them. So we also we cannot just say, okay, so everyone now is going to use public transportation, but if some people are going to be worse off, we need to understand those impacts, because that will have an implication on why people are choosing that mode of transportation or not. And then that's what I did for this work, was to analyze the literature review to see what we know about how these technologies and services affect energy and emissions. So the results of the analysis, it was a detailed literature review. I analyzed, I don't know, around 100 or more papers, and that is still going on because, of course, I'm going to finish my thesis hopefully next year. And when that happens, many more works are coming out, and I'm always updating this as it should be. So far, the results that we have is that the directions of the effects, they're fairly the same across the studies, but the magnitude is influenced by the assumptions made. Because some studies, they are about simulations, others they use simulations, the methods. Other studies, they use survey analysis, and other studies, they do literature review as well. So the size of the effects, they may vary a little bit among studies, but the direction is pretty much the same. That's what I was able to find. So this table summarizes what I found so far about these, how these technologies and services affect the variables of interest. So for instance, so we have car sharing and ride hailing and autonomous vehicles. And we have the impacts of these technologies and services on vehicle kilometers travel or miles travel, depending on where you are, and the impacts on CO2 emissions, other transit modes, and economic welfare. There are other impacts as well on safety, and because some studies, they analyze how these technologies and services, they impact safety and how impact engine efficiency and how they impact other variables. But these are the ones that I thought it would be more interesting to discuss today. All the other impacts are in the paper that is attached to this presentation. So for instance, starting with car sharing, the impact about vehicle miles travel, what was found that actually vehicle ownership first, sorry. So car sharing, people that they participate in car sharing, they tend to reduce the vehicle ownership. That so people they shed cars. So pretty much they say, I'm going to sign up to a car sharing service. I'm going to use less cars. I don't want to own a car anymore. For ride hailing, that was inconclusive. So not necessarily people that they sign up for a ride hailing scheme like Uber or Lyft, they give up their car or the intention to buy a car. That's not very conclusive from the literature review. About autonomous vehicles, so the impact of autonomous vehicles on vehicle ownership is not very well studied. What has been studied is how autonomous vehicles will provide mobility to people that they do not have mobility today, to the underserved populations, but about people giving up the idea of buying a car or giving up a car altogether, that hasn't been studied as much. But some papers show that shared autonomous vehicles, they do decrease car ownership.
So Tatiana, you've used 18 minutes for your information. So you have 2 more minutes left.
Okay, I was afraid of talking too fast and the other way around happened, I'm sorry. So, and about kilometers travel, car sharing, they decrease the miles travel, ride hailing, actually they do increase because of that heading, and autonomous vehicles, they increase the miles travel. They share autonomous vehicles, they mitigate a little bit the impacts. And these, so miles travel, they're going to have an impact on CO2 emissions. So in the case of ride hailing, the pool, if it's share ride hailing, they're going to lower the emissions. And for car sharing also, because it reduces vehicles miles travel, it's going to lower the emissions as well as autonomous vehicles. About other transit modes, the car sharing, so these technologies and services, they may substitute or complement with other transit modes. Autonomous vehicles, it was found that they substitute other transit modes, and ride hailing, depending, it mostly substitutes as well. And there are some impacts according to which service they substitute. And car sharing, they can complement or substitute. And economic welfare pretty much increase in all the cases because people, they're better off consuming these services. And then this pretty much just summarizes what is in the table for the 3 technologies and services. And in conclusion is that the impacts on energy consumption and emissions, they have been studied, but impacts on economic welfare, there are some indication of how these new mobility technologies and services, they're going to impact economic welfare, but it's not very well understood how it's going to match with the energy consumption and emissions. So this interaction that is going to be studied by myself in my PhD thesis, and this is pretty much what I'm going to do next. So actually what I am already doing in my PhD thesis, that I'm going to develop an energy systems model that I'm going to put together with an economic model to understand how these new mobility technologies and services, they are going to contribute to climate change mitigation by reducing energy consumption and emissions, and how that is going to impact economic welfare in Rio de Janeiro, which is the case study that I chose to study for my PhD thesis. So pretty much that's it. I'm done. This is done and this is done. I'm developing the general equilibrium model now, and that's it. Sorry.
Okay. No problem. Thank you. Thank you, Tatiana.
Thank you.
So, I leave the floor open for questions. People that want to ask questions, please go ahead, and you can also type in questions already in the chat box so that I know that you want to ask a question. If there's no questions, let me start with first one, Tatiana. So when you do your literature review, it's always interesting to see what your methodology is in doing the literature review. What literature did you focus on? What kind of journals? And what were sort of the keywords that you were searching for in doing that literature review?
Yes, so my focus was how car sharing and ride hailing and autonomous vehicles, they were being studied in a sense that how they contribute to change energy consumption and then emissions. So many studies, they talk about car ownership or emissions, or car ownership, but or other studies, they talk about how these modes, they substitute other transit modes, but there was no emission analysis. So I try I funnel my research to how they're going to impact emissions and how they're going to impact energy consumption and emissions. And then also what is the interaction with other transit modes, as well as the economic impact. Many studies, they had impacts not on overall welfare, but more about consumption behavioral aspects. So why people, it wasn't much behavioral aspect, it was more like the profile of people who use these mobility technologies and services. But actually the economic impact, that wasn't very much studied in the literature I reviewed.
Yeah, thank you, Tatiana. My question is more directing you towards methodologies for research reviews. There are systematic literature reviews in which you would basically go take a database, set criteria for the kinds of keywords that you'd be searching for, select also the kind of journals that you will be focusing on, and it helps you also to be sure that you cover the domain and that you understand what the field is speaking about, in which, you know, historically, but also the dominance of certain topics, etc. Yes. But it seems like you use more of a snowballing type of approach, where you use one paper to then go to other papers and sort of search through the literature that way.
I did both, actually, because there are some, so I focus on the transportation journals and the energy journals and also the economic journals. So for instance, there are many transportation journals at Elsevier and Scopus, and also Web of Science. So I knew which journals they were, so I focused on those journals, and I searched for the keywords were emissions and energy consumption and new mobility services and Uber and autonomous vehicles. And then I did the same for the journals that are more related to energy, like Applied Energy or Energy Policy, and I did the same for the economic journals, American Economic Review, Journal of Political Economy, and so on and so forth. So yeah. I have these three.
But so the idea would be, it's always interesting in writing up your thesis or any paper to document the approach that you took. Okay, so we have to switch to the next presentation, unfortunately. Excuse me. Thank you so much, Tatiana, for your presentation and your enthusiasm. There was one more question by Annie. I'm sorry, I only see it now, but perhaps, Annie, you could just share your question in the chat box with Tatiana. This is, by the way, also the case for everyone. I think any feedback that you can still give is greatly appreciated, I guess. So thank you so much once again, Tatiana. And now we can pass to Francisco. Francisco, you're already sharing your presentation, so the floor is yours.
Okay, thank you very much. Sorry again for the little problem we had, but okay, now I'm connected to my phone. Hopefully I won't have any problem. Thanks, Jan. So my name is Francisco José Santos. I'm a PhD student at CentraleSupelec. I'm working under the supervision of Dr. Isabel Nicolai. Today I'm presenting the first paper to be included in my doctoral thesis entitled Business Model Innovation in the EV Ecosystem. Okay, this is an overview of the presentation. First, I'll talk about the context, the motivation for the study, then how we build a business model innovation framework that we are proposing to study the case of the electric vehicle ecosystem. And finally, I will finish with conclusions and further studies for this. Okay, so first of all, the context. So as we all know, there is a need to decarbonize the automobile industry. By this, it means that there must be a scale up of EV adoption that is even forced by regulation. By this, I mean that there are some strict CO2 emission standards that are already in place, and also some public policies that incentivize this EV adoption. Up to date, we are seeing that EVs are becoming with time more and more competitive on a total cost of ownership. This mainly because of the advancements in technology, especially in batteries, that have becoming less costly. Also, it's a fact that in 2020, despite the COVID-19 pandemic, we had an increasement in EV registrations, even though that the overall car market contracted a bit. It didn't happen with the registration of electric vehicles, and therefore we've seen OEMs that have set electrification targets to comply with these different scenarios. As we can see here on the right, by the year 2025, the targets we're expecting to have around 75 million electric vehicles in the streets, which it will mean a huge ramp up from what we have today. And this acceleration will grow exponentially. Okay, so what is the motivation for this study? Of course, it's the new electric mobility and the transition that will require a fundamental change in the automotive industry. Up to date, we can say that the commercialization of EVs has been ineffective because car manufacturers are taking business as usual. By this, I mean, for example, building their cars as they were building internal combustion engines and just adding the batteries as another module to be integrated in the factory, for example. Nevertheless, EVs are different. They integrate a diversity of previously independent actors, and there will be some other actors that will emerge. And also because of its connectivity and technology, this would allow for new business opportunities that could be looked for. We state that then that classical business models for internal combustion engine vehicles can be transferred to a new electric mobility. What is my research question? So the EV industry faces a critical challenge, but it's not from an individual firm perspective. It is a more complex dynamic context. This is why we said that the business model construct must be enlarged from the perspective of the value chain to that of a value ecosystem. And to do this, the focus of studying is to shift from a focal firm to the constellation of actors and the level of analysis from firm strategy to the value proposition. This brings me to the research question that the paper wants to address, that is how to design innovative business models at the interface of the new electric vehicle ecosystem. For this, I would like to explain our understanding of the evolution of the business model concept. So the value chain perspective, where the business model boundaries are constrained to the company, to the focal firm, and all the processes and mechanisms are for the use of the internal firm. Then with the first steps in open innovation, companies started to look at their environment, crossing boundaries of the firm, to look for collaborations to create value. Nevertheless, the competitive strategy was still focusing on the focal firm to get advantage over the others. And what we are looking for is what we call the business ecosystem, that it's a business model that could fit a shared entity, where the importance of the company business model, the focal firm, is as important as that of the ecosystem. Okay, what is our objective? In terms of studies of business models for electric mobility, we've seen that they are mainly considering a linear value chain approach. And in this way, the multi-party interdependence, the flow of activities, and the realignment of the positions of the participants along the rigid structure of the value chain are out of scope. Our objective is then to analyze the EV industry through the lens of its ecosystem in order to step up from a static ontology of business model and to propose a dynamic process of business model design for the EV ecosystem. Okay, in order to do this, we build a business model in a framework based on 3 points. The first is we define the business model and business model innovation construct using the system of activities, and using first here the definition from TIS, saying that the business model is the architecture of a firm's value creation, delivery, and capture mechanism. In consequence, the business model innovation is defined as design, novel, and non-trivial changes to the key elements of a firm's business model and or the architecture that links these elements. This definition from the study from Foss and Saevi. We want to stress our notion of what the architecture means for us, which is the mapping of the set of the relations that happen among the elements of a system, where these relations can be characterized in terms of directionality, the strength of their complementarities, and the content. And finally, well, the complementarity is a key dimension of our business model construct. Then we're following a service dominant logic as a driver for the design. We know that now companies in the traditional value chain are pushing to a more service-based mindset. Doing products right now, it's becoming less profitable. Nevertheless, in this way on this logic, the value is not conceived within a focus of a single firm, but from a collaborative value network, what we call the value network. This way, companies need learn more about their customers in order to work with them to be better aligned to propose a value, well, for the customer value proposition that they will look for. Okay, and what would be new with this business model innovation analysis? What are the elements that will shape our construct? So there will be the interaction between the three value elements that we mentioned that will be analyzed: the value proposition innovation on the top of the image, the value creation and the delivery innovation, and the value capture innovation. If we contrast this with the value configurations included in classical elements of business model, like the business model canvas, for example, we can show how the different value configurations will behave. First, we have the value proposition, which will be at the center of all the elements and will be affected, let's say, by all of the other elements and will be directly linked to the user, to the market segment. Then we have the value creation and delivery innovation. That is the part that we're gonna deepen in our study and considering the value network. The value network will be the one that will create and deliver the values, will connect the structure of the value chain with the user, with the market segment, and will directly affect the value proposition. And finally, the value capture innovation, which would consider the cost and the profit that would also affect, let's say, the value proposition in a way. We are also adding an axis of strategy called ecosystem strategy. And this ecosystem strategy will look for the alignment of the participants that are included in the ecosystem. And it will look for value creation opportunities, and we'll try to get agreements on how to capture this value between them. And also, as conditions are going to change, this alignment must be maintained. Therefore, we have to consider the evolution of the ecosystem in order to readapt our business models. And third, in order to explain or to analyze the value network, both the concept of the business ecosystem. By this, we attack the definition that given by Adler, that he treats the ecosystem as a structure, and he defined this as the alignment structure of the multilateral set of partners that need to interact in order for a focal value proposition to materialize. There are four elements that characterize the value blueprint: activities, actors, positions, and links. And then we have to define the ecosystem strategy for the focal firm, which is the way in which the focal firm approaches this alignment of partners in order to secure a role in the competitive ecosystem. So what is going to change with this business ecosystem perspective? We'll have a wide lens perspective for collective value. The delivery of the value proposition will depend on the ability to align the strategy, and the success of the innovation depends on the complementors. As we said before, the ecosystem's evolution will help the participants or the actors to readapt their business models in order to adapt to the changing conditions. In the right part, we can see the elements proposed in our business model innovation framework: the value proposition, the activities, the actors, and the position in the ecosystem, which will shape the value network and also, of course, the value creation and the delivery. And finally, the links and the strategy in order to shape the value capture mechanisms. I will apply it later on an example. Now we're analyzing the case of the EV ecosystem. So what is changing? Before, with internal combustion engine vehicles, we have a traditional product-oriented business model with a value chain configuration in an industry that was already established. Now EVs will target innovative service-oriented business models with a value network configuration in an ecosystem that is just starting, that is in an early stage. And we'll have stakeholders from different industries that will merge together in an innovation interface. And we'll have critical limitations from the new components that we will have in EVs, that are the battery and the charging. As we can see here, the EV ecosystem will include the three segments that I mentioned, the vehicles, which will include the vehicle with the battery, then the energy interface that includes the energy utilities and the charging infrastructure that needs to be developed. And on the services part, we include the users and the aggregators or complementers. Also in the intersections, we can see the potential services that could emerge in the intersection between these interfaces of the EV ecosystem. And in order to have a visual tool of what are the main actors in the potential services, we present this generic EV ecosystem map with the three interfaces that we mentioned. We have on the left side, the vehicle plus the battery, also in considering the part of the supply chain and the battery recycling service that we'll have to consider in the future. Then on the right part, the energy interface with the energy producers and the TSOs and DSOs that will provide the electricity, and of course the charging station network infrastructure that must be developed and installed. So we consider the supply part. And in the middle, the service interfaces that includes the complementers and aggregators that are the ones that's gonna serve the outcome to the EV users, let's say, and a potential array of services, mobility services, grid integration, or the supply of energy, for example. We also include R&D and regulators, which will be also very important, the regulators for the interaction with the EV ecosystem. Of course, this ecosystem has constraints. As we said, the main problem right now for us is the range anxiety, which is a problem of the batteries and the charging infrastructure. Nevertheless, on the last years, we've seen an increased progress on the battery technology. We see Tesla with one of the best battery technologies available. They also managed to industrialize their lithium-ion battery in order to take advantage of economies of scale, in order to reduce costs. We also have promising new technologies like the sodium-ion, which will promise higher energy densities. So I think we're making progress on this part. Nevertheless, there's the problem of the charging infrastructure, that although there have been first efforts from governments and firms to start with the investments, initial investment needed, there is a huge amount of infrastructure that must be developed. And as we thought, this will accelerate exponentially in the following years. And because of these high investments and high risk that we have, the problem remains on who owns the value created and how to capture part of this value. So in order to attack this, we are making an application of our street charging. We know that right now, most of the charging is done at home and work. Therefore, the deployment of the public accessible charging infrastructure will be critical. We have the example of European countries that have failed to meet the recommended targets of 1 public charger per 10 electric vehicles for the year 2020. So even though now that we have a very low demand, well, still a low demand on electric vehicles, we haven't even met the recommended targets. Therefore, we have to consider this very seriously. And of course, public fast chargers will encourage later adopters with no access to private charging, and it will account for longer trips in order to foster adoption. Okay, so then we apply the case into our elements of we presented in order to better illustrate the elements that are included in our proposition, especially here in the middle that I will explain now. First, we define our value proposition for the public street charging, which is charging infrastructure in public areas with public access. Then we need to define what are the activities needed for this value proposition to materialize. So here we talk about the development of the infrastructure, the network costs and the distribution services, the charging services for EV owners, and the change in regulation. And then each of these activities, who will perform them? So now we mentioned the actors that will be part of this ecosystem, the DSOs, the charging point infrastructure, or the people who's gonna be in charge of developing. A new player that will emerge, that is the electric vehicle supply aggregator, which will be operating the charging points and aggregating vehicles for its supply, the EV owner and public authorities. And here in the part which actor will hand off to which actor, what is the directionality of this transaction, what is the strength, and then as we can see here, for example, for the infrastructure development, we're considering for this scenario that DSOs are in charge of developing the infrastructure, as is happening with some companies in Germany, for example, just to illustrate an example. And what are the links on the column E? So in this case, it can be monetary and non-monetary value units. We're saying that for this type of infrastructure and money. And then finally, what is the strategy? What is the focal firm of study will do for the alignment of these partners, even though they are not directly connected to the focal firm? This will allow to look for interdependencies along the activities. So we define all the activities, all the flows of value, and then what we are looking is to have an ecosystem mapping. The mapping all these activities in an ecosystem, and the part that the actors and also so here we map the different participants that we had already. We are saying that the DSO is going to take the paper, of installing and developing the charging point station, the infrastructure. Therefore, we can see how these flows of values will go or will configure. We will also have we can see some potential services that could emerge as an adjacent part or something that could complement the business model, such as mobility services, or creating integration in a later stage, let's say, for DSOs would be interesting, for example. And we have in the center also the new player that emerged, which is the electric vehicle aggregator, and we have to think who's gonna take this position. Is it a new player that will come, a new company, or for example, we've seen some suppositions where car manufacturers could bundle services with the car, let's say selling the car plus the charging infrastructure. So therefore, taking the strategy.
Francisco, I'm just letting you know that you have used 19. Francisco, you have used 19 minutes, so you need to wrap up your.
Their flows of value, which will be interesting.
Francisco, can you hear me?
Thank you. I'll just close up.
Okay.
Yes.
Yeah. So you need to wrap up because you've used 20 minutes.
Yeah.
Okay. So the last part of the
Tesla.
You know that your connection is very unstable, unfortunately. So maybe you just turn off your camera. That will make it easier, maybe to have a stable connection. Any questions for Francisco from anyone? Please don't hesitate to type them also in the chat box if you could. Sorry that I interrupted you so abruptly, Francisco, but you just came to
sorry for my connection.
No problem. So let me maybe start with one question, Francisco.
Yeah.
I hope the connection is stable, and please, everyone present, don't hesitate to ask questions too. So thank you very much for a very interesting presentation. You started out your presentation with an assumption, which is that the future of EVs will be an ecosystem business model for the automotive industry. Why is that the case? Why is it that they cannot stay in the linear business model that they have right now? Or, you know, in a way, there's already a lot of ecosystem elements in the current business models of the OEMs. They are all interconnected. They all share manufacturing, R&D, standards, reliance on the same complementary assets. So, I mean, the question for me is, I understand your analysis, but why would it be that, and I think that's an interesting question in of its own, why do you think that they will shift from something that's a linear value chain to a more diffuse business ecosystem model?
My connection was not stable, but can you?
No. Yeah, I'm not sure the connection is stable, Francisco.
Yeah.
So, yeah. So maybe what I propose is that we can continue the exchange through chat. I think this is one of the great things that we can do with this Zoom, is that we can still have a conversation even though we don't have to do it in a give and take, and we can still do it in a way that's shared by everyone. So unless you still want to, maybe you want to stop sharing your presentation, that's going to take away or give some bandwidth if you want to answer your question. If not, then we can switch to the next presentation.
Yeah, I'm trying to do that right now, but I don't know if it will. Yeah, because I have here that my connection is.
Mm-hmm.
Yeah.
What I propose is that we switch to the next presentation, and if there's some time left at the end, we can maybe come back to your questions. And for everyone present, please don't hesitate to ask questions through the chat. I think that's the best option that we have. I
agree. I'll be checking the chat here and looking for my connection. I'm really sorry about this. But yeah, I am here and I can continue the conversation in the chat. Okay?
Excellent.
Great. Thank you, everybody. Sorry.
No problem. We're all struggling. So
yeah,
I think we can then switch to our third presentation, which is a presentation by Alexandre Cambo from the IFP Energy, Benoît Chaise, and Johanna Ettner. So Alexandre, are you going to present? Okay.
Yes. Hello, everyone. Can you see me and hear me fine?
That is all perfect. Thank you, Alexandre.
Okay. Let me put my presentation full screen. So, hello, everyone. My name is Alexandre Cambo. I'm a PhD student at IFP Énergie Nouvelle. And I am going to present my upcoming article called Preferences, or my upcoming paper called Preferences for Alternative Vehicle, Analysis of Barriers to Adoption through a Discrete Choice Experiment, co-written with Benoît Chaise and Johanna Ettner. So first, I will start with an introduction on the topic and talk about the state of the literature and the innovations brought by our paper. So the aim of this paper is to reveal preferences for different vehicle technologies, and we used a survey using the discrete choice experiment methodology. So this experiment was made in January 2021 among 1,000 respondents representative of the French population. So let's talk a bit about the context of the experiment. So car passenger traffic accounts for about 12% of the greenhouse gas emissions generated by EU countries and 15% worldwide. The EU has reduced its emissions by 23% since 1990, while emissions from road transport have increased by about 20%. In France, the transportation sector is responsible for 30% of the national greenhouse gas emissions, which makes the transportation sector the biggest greenhouse gas emitting sector in France. France has formulated the strategy bas carbone that aims to reduce by 28% the sector's carbon emissions by 2030. And in order to achieve those goals, the French government has set an aim to transition towards cleaner transportation technologies. However, in 2019, there were only 200,000 electric vehicles out of 32 million vehicles in the French fleet. So our paper asks, what are the main reasons for the current low electric vehicle adoption rates? And what can we do in terms of public policies in order to overcome the barriers to entry and increase electric vehicle adoption rates? So there is an extensive literature on the topic using choice experiments in the transport field. However, so far there have been none on the specific French case, and none of the discrete choice experiments in this field have used uncertainty or analysis of risk attitudes in this experiment. And in this experiment, we will investigate the heterogeneity in preferences and the socio-economic determinants and risk attitudes on the preferences for electric vehicles. So what's the evidence from the literature? So this literature agrees that the purchase price, vehicle ownership cost, range, and charging time have the greatest effect on vehicle adoption rates. The low proportion of charging stations available or the detour time taken to find one is also a significant adoption factor for battery electric vehicles. And this is why some authors agree that hybrid vehicles are considered to be the most likely alternative to conventional vehicles to be chosen. So how does our paper set itself apart from the literature? Well, firstly, we use the assumptions that according to different vehicle sizes, there are different usages and different preferences. So this is why we divide our sample into two subsamples, one for small vehicles typically used in the city, and the other for medium vehicles and all other vehicles that we put into this category, as we assume that there are two main vehicle usage types. So the second way our paper innovates is that one of our attributes in our choice experiment doesn't use a fixed value. So in the literature, we find that contrary to other fields of transportation research, the field of vehicle preferences lacks research about the influence of attribute uncertainty on adoption rates. Excluding uncertainty when talking about vehicle range, charging availability may reduce realism of presented choice tasks and thus may reduce the quality of the answers. So now let's talk about how we made this discrete choice experiment. So firstly, what is a choice experiment? So the discrete choice experiment method is based on the utility framework in microeconomics by Lancaster and McFadden, and from the stated preference methods and environmental economics that seeks to ask respondents about the preferences instead of revealing them through observations of the market. During the design of the experiment, we choose a number of attributes, the level of these attributes for each scenario. In order to optimize the combinations of attributes levels for each scenario, we create an experimental design which dictates the contents of each scenario. In order to optimize the combinations of attributes level for each scenario, we create an experimental design which dictates the contents of the scenario. The survey consists of a discrete choice experiment called DCE, plus other questions we ask respondents. We chose to administer this experiment through an online survey service. And finally, for the analysis, we use logistics methods, where the conditional logit model outputs the sample average preferences, while the mixed logit or Latin class model accounts for differences in preferences between respondents. And finally, the ICLV model determines the effect of psychological positions or attitudes on preferences. So because this is current work in progress, we will only be showing the results from the mixed logit model in this presentation that accounts for heterogeneity of preferences. Okay, so here is an overview. So our design uses 6 attributes with 3 to 6 levels. We have 8 choices between 3 labeled alternatives. We use 3 blocks containing 8 cards using D-efficient designs with 1,022 respondents using an online survey service. And I already talked about the econometric analysis. So we saw that citizens have to choose between a battery electric vehicle, a plug-in hybrid vehicle, and a conventional vehicle. The attributes that we use here are the monetary costs, which are purchase cost, fuel cost, and maintenance cost, while the others include vehicle range, environmental label. So this is our way of simplifying the level of greenhouse gas emissions to respondents, and the proportion of refueling infrastructure available. So let's look at an example of a choice card. So here in green, you can see our diesel gasoline vehicle, which is our conventional vehicle. So this vehicle has a purchase price of 20,000 euros, an estimated annual fuel cost of 1,000 euros for driving 10,000 kilometers, an estimated annual maintenance cost of 400 euros per year, a driving range of 700 kilometers before needing to be refueled, and a level of infrastructure. So this is the picture that depicts that all gas stations are available to refuel the vehicle. And finally, the vehicle has a D environmental label when looking at its greenhouse gas emissions. I forgot to mention, but the environmental label only takes into account emissions during use and not the emissions of the vehicle during manufacturing or recycling. Okay, so if we compare to the electric vehicle and focus on the level of infrastructure, we can see that it has a different image. This is how we represent our uncertainty with a level that depicts one scenario where all stations will have electric fast charging and another where only 3 out of 5 stations will be equipped. So we will talk more about these attributes in the later slides. So here's the hybrid vehicle card. It is very similar to the conventional one. So I will continue on. Okay, so now let's talk how we chose the attributes and their levels. So in a discrete choice experiment, the number of attributes must be limited in order to avoid cognitive burden without omitting any fundamental attribute. The choice of the attributes and levels were based on the literature and on recommendations from transport experts. So the literature seems to agree that using 4 to 8 attributes is a good number for a choice experiment. We have thus decided to include 6 attributes. So the attributes level were designed based on the value of a representative vehicle for each size and technology from the recommendation of an expert in the transport field. And yes, so now I will detail the infrastructure amount. So we show the proportion of fast charging stations as a ratio out of 5 of all service stations. We assume that vehicle users won't be using public charging infrastructure if it takes longer than 30 minutes to charge. A score of 3 out of 5, as you can see on the right on the picture without risk, would mean that out of all the service stations available in my area, only 3 are equipped for electric vehicle. If I go to the wrong station, I will lose time by searching for another one. However, we don't know how many stations we will have in the near future. This depends on public and private infrastructure investment. Thus, we present this uncertainty through the presentation of scenarios that are equally likely to be realized. This is shown through the picture on the left with risk, with the arrows representing a 15% chance of the scenario happening. So as you can see, in certain cases, the predictions are certain, while in other cases, experts make predictions according to two scenarios that are equally probable of being realized. Okay, so now let's talk about the experimental design. So it's impossible to include all the combinations of levels into our choice experiment, or our questionnaire will be far too heavy to answer. So what we do is we use an experimental design using a d-optimal criterion, where we minimize the size of the variance-covariance matrix of parameters given a prior for coefficients. We obtained the first version with 24 choice sets, which were blocked into 3 blocks with 8 choice sets per respondent. This first version has been administered to a test sample comprising of 100 respondents to estimate prior coefficients in November 2020 and to test if the experiment was functioning correctly. The results were then used to formulate the current design. Okay, so let's talk about the questionnaire and data collection. So to sum up, this questionnaire lasted less than 20 minutes. We gave a description of the survey, where we gave a description of the attributes and presented an example of a choice task, as you can see an example on the right. Respondents were presented 8 choice cards where they had to choose between one of the 3 vehicles. So adding to that, we ask additional questions to respondents if they only chose the conventional vehicle in all choice sets, as this may be considered a protest answer. General questions were also asked regarding the respondents' characteristics, and we also asked final question on social demographic situation, transport, risk, and environmental behavior. So as I said before, it took place in January, and we used a professionally selected sample to represent the French population, with half of the sample in the small choice set and the other in the other vehicle choice set, also called medium choice set. So now I will present the results of the econometric analysis. But first, let's give a talk about the theoretical framework of this analysis. So we use the conditional logit model that is based on revealed preference theory, where if option B is preferred over option A, then the utility of B must be higher than the utility of A. This utility comprises of the option's characteristics and an error term. We thus estimate the likelihood to choose an option based on this option's utility. We start with a simple linear model to estimate the results of this prior survey, where socio-economic and psychological variables were not included. So as you can see in orange, you can see in the equation are monetary attributes. You can see then in purple the range, the infrastructure level, and the environmental label. Following that, we used a random parameter logit model, where the difference with a conditional logit model is that we allow for heterogeneity and preferences between individuals. In our model, we assume that our parameters are random and follow the properties of a normal distribution. So to sum up, we make respondents choose between alternatives according to their attributes levels, and using the answers from the discrete choice experiment and the respondent's socioeconomic characteristics, we model the respondent's probability to choose an alternative according to the attributes and their characteristics. Okay, so now I will present the estimation results. So note that I show here the results from the 2 samples side to side. On the left, you can see the results from the small sample, and on the right, the results from the medium sample. The attributes without stars are not statistically significant, meaning that the results have shown that they weren't taken into account when choosing between vehicles. The more a coefficient has stars, the more statistically significant it is. We chose to show T ratios in parentheses as they represent the ratio between the coefficients and the standard error and show the relative importance of the attributes. The results on the left are the coefficient, while the one on the right is the coefficient for the standard error, which represents the amount of heterogeneity of the attribute. So I will start by talking about the ASCs. So what are ASCs? These are alternative specific constants. They take a value of 1 for their own vehicle type, and they capture the effects of all the vehicle characteristics that are not present in our survey, such as the ease of use of a vehicle or the pleasure of driving it, for example. For small vehicles, only...
So Alexander, you've used 17 minutes just for your information.
For small vehicles, only the ASCs for hybrid vehicles is significant and positive. This means that with all attributes taken into account, users preferred hybrid vehicles over conventional ones. For medium vehicles, the ASCs are negative, which is common in the literature, meaning that users preferred conventional vehicles over alternative ones after all attributes were taken into account. So we can see right from the start that there is a difference in preferences and in usage between the small and medium sample, which show a difference in preferences between the different technology type. Now, if we look at the monetary attributes, we can see that, purchase cost, fuel cost, and maintenance cost are all negative and significant, which confirms intuition and the results from the literature. However, when looking at the T ratios in orange, we can see that users saw as a priority purchase cost over fuel and maintenance cost, as the absolute value of the purchase price is higher. So we can see that according to our results, policies that focus more on purchase price will be more effective than ones that focused on fuel or maintenance cost. Following that, if we look at the vehicle range, we can see that for both categories, it is positive and significant. Looking at the environmental label, we can see that it is negative and significant for both categories, meaning that users did take into account level of emissions and preferred vehicles with lower emissions. We could say that maybe users in our sample care about the environment or were fearful about the future restrictions on vehicles with higher emissions. Finally, let's look at the recharging infrastructure. So we need to note that we put this attribute in a discrete format in order to see the effects of individual levels of stations. We present the dummies for all the levels except the highest one, which is used as a reference for the results presented here. Thus, all the coefficients are in comparison with the full level of recharging infrastructure, which is the missing level in order to avoid the dummy trap. We see that for the small sample, the first 3 lower levels are negative and significant, while the remaining 2 are not significant. This means that small users didn't mind having 3 out of 5 stations over full stations. Whereas for the medium sample on the right, we see that all levels are negative and significant, meaning that medium vehicle users would only accept vehicles with full recharging infrastructure level. So these results show a difference in usage type and needs between small and medium vehicles, especially for the medium vehicles where you can see that users would not accept any infrastructure level other than a full level of infrastructure available with certainty. This shows
Alexander,
that...
you're running out of time. So if you could...
So I'll go directly to the lessons for policymakers. So the lessons for our experiments is that high purchase price is the main barrier for widespread electric vehicle adoption. Subsidies for alternative vehicles and penalties for conventional vehicles will be more effective than fuel taxes in order to help promote alternative vehicle adoption. And the uncertainty surrounding the future level of charging infrastructure is a factor preventing electric vehicle adoption, especially for medium vehicle users. And finally, policymakers need to invest in charging infrastructure in order to help promote electric vehicles, especially for medium users outside urban areas. Thank you for listening. I will now be taking questions.
All right. Thank you very much, Alexandre. There's already 2 questions. So maybe start with James's question. You can perhaps read them in the chat box yourself, unless,
okay.
yeah. Unless James, you want to read it out loud?
I'll read it. It's fine.
Okay.
So James asked, EVs are expected to have lower maintenance costs, but is there a reliable source for this? So I am on this subject. I precisely asked the expert on the transfer field at my company, EFP Énergie Nouvelle. He answered me that electric vehicles are expected to have lower maintenance costs because firstly, they have less usage of brake, braking the vehicle, and also there is less pieces to be replaced in the vehicle compared to conventional ones. As for reliable sources for this, right now I can't give you any. Maybe I can come back to you and ask the experts in the transport fields. So sorry if I can't answer this question.
That's perfect, Alexandre. Thank you very much. I'm just we were thinking about including maintenance costs in our own discrete choice experiments, and we actually couldn't find a source to back it up. But intuitively, it does make sense that it would be a lot less maintenance over 5 years with a lot less components. But it was actually quite challenging to include it in an RTC. But thank you. We might follow up afterwards.
Yes, definitely send me an email. I'll send you the sources I can.
Great, and thanks for your presentation. Really interesting. Thank you.
Thank you. The second question is by Annie. Do you know whether respondents have experience with electric hybrid cars or whether they own small, medium cars? There are quite many monetary attributes. Could this be a problem instead of a summary cost? Okay, real quickly. So we did ask this question. I shared again my presentation with an appendix with all the questions asked in our experiment. So yes, we did ask respondents if they have driven an electric or hybrid car before, or whether they own a car before. We also asked at the start of the experiment what kind of car they would be most likely to purchase in the future. For your second question, there are quite many monetary attributes. Could this be a problem instead of a summary cost? So in the literature, there are 2 sides. Some people do include maintenance costs. Some other people choose to sum up fuel costs and maintenance costs into a single attribute with what they usually call it yearly usage cost. We choose to use maintenance cost by the assumption that people that are regular vehicle users would certainly take this into account when looking at preferences for vehicle. And our results have shown that it has been statistically significant. Also, in our experiment, we asked questions if the respondents had understood or if they found it difficult to answer the choice experiment, and the feedback was mainly positive. So I don't think it was a problem for our respondents. I hope I answered your question. Final question by Tatiana.
I'm just trying to figure out, just because normally we've come to the end of the Q&A as well,
Okay.
but I don't see the presenters for the fourth presentation present here, unless I'm mistaken. Ali, Carla, or Hannes, we're supposed to present now. Are you present here?
I'm here. I'm here.
I'm
Okay.
sorry. Okay, Carla, thank you so much. Okay, it was Carla Mendes, and that was not showing up on my screen. So
Okay, I'll answer the last question in the chat, no problem.
Okay, thank you. And everyone else, please continue the questions indeed and the suggestions in the chat. So thank you so much, Alexandre. Very interesting presentation. Carla, the floor is yours.
Okay, so can you hear me perfectly?
Perfect.
I hope so.
Yep.
Let me just share my screen. Then. Okay, put it on presenter mode. I hope it's working to everyone now.
It is, at least for me.
Okay, great. So welcome to everybody. My name is Carla. I'm a PhD student at the University of Basel. And I'm here today to present a paper that studies the impact of electrical mobility that I will call EVs from now on in Switzerland. This is a work done by my colleague Ali and together with my professor Hannes. So in this presentation, I'm just showing you like a brief overview about my motivation and the contribution of this paper, then present the model setup and the data I used, and finally shows you the results and conclude. So regarding the motivation, following the same steps as many European countries, Switzerland is now under extensive reforms on its energy system. And the Swiss energy strategy up to 2050 is based on three main pillars: increasing energy efficiency, increasing the use of renewable energy, and withdrawal from nuclear energy. So what does that mean in terms of the Swiss energy portfolio? So if we look to these both figures here, we see that the capacity in the Swiss energy market is mostly provided by 56% of hydro generation and 35% of nuclear, which sum up at around 91% of total generation that comes from these two sources. So if we withdraw the nuclear power from the system, and if we look into the yearly profile in the second figure, we see that we are deleting most of the conventional technologies that we have at the moment, and basing our system mostly on the hydro profiles that are not sufficient to cover the load in winter, but also become independent of imports and renewables energy systems that are quite variable. In terms of the transportation, Switzerland uses like kind of 38% of the energy used for the transportation sector, that is in here, and which represents about 40% of Swiss CO2 emissions. And this tends, so the final consumption in the transportation sector tends to increase in the latest years. So mobility is of central importance of the Swiss energy transition and to climate policy in order to reduce CO2 emissions and to compensate for an expected increase in CO2 in the electricity sector due to import of energy from gas power plants. So what we intend to respond with this paper is to study the possible future interactions of EVs in the Swiss power system in terms of dispatch power plants, integration of renewables, change on the demand side, variable charging costs, and CO2 emissions. So in order to do that, we need an integrated approach that combines not only technology aspects, but also economic and environmental ones. So following this up, the model that we use or that we create is the Swiss mod. Swiss mod is a numerical optimization model that simultaneously optimizes power plant dispatch and charging EVs, taking into account the thermal power plant portfolio, the renewables in feed, complex hydrostructure, and grid connections of electrical mobility. The model has an hourly resolution and is sold for a full year. It has a detailed representation of the Swiss power systems, around 230 nodes with 400 lines. And we aggregate the neighboring countries and most of the European countries too. Since hydropower is very important in Switzerland, we also introduced in the model around 200 cascades with approximately 400 power plants, which represents 95% of production. So basically what we do is to connect upper water nodes to power plants that will be connected to lower water nodes, and we kind of represent hydro cascades, like as you see in this picture in the middle. Finally, so how do we introduce electrical mobility in the system? So we introduced this charge variable that we, in the demand supply balance, that will give us what will be the demand for electrical mobility in the system. For vehicle to grid, we also have another one called this charge that will give us how much electricity will be put back into the grid if it is needed. Of course, this is constrained by the storage equation that gives us that each hour will be equals to the previous storage of the vehicle plus the charge minus the charge if the vehicle was driving at that moment, subject to the battery constraints and also charging rates constraints. So regarding the data that we use in the model, so to get the electricity supply and demand for the future years up to 2040, we get that information from the STEM model that is developed by the PSI. And for the trip characteristics, which mean like which kind of cars and how many kilometers will be driven by the day, we use from the BEDM, that is an agent-based modeling that studies behavior theory, discrete choice, and mobility choice. And all this data will be integrated in Swiss mod, the model that I explained before. Regarding the scenarios, we used two main ones. So EPOL is a more conservative scenario that measures the Swiss strategy up to 2050 without a specific CO2 target, and the CLI is a more ambitious one that tries to reach carbon neutrality by 2050. Plus, we also add some dimensions to these scenarios regarding technology availability. So how many vehicles we will have in the system, which kind of vehicles, and also some kind of climate policy, so CO2 emission targets and renewables capacity installments. Finally, after we have the combination of a couple of these scenarios, we include them in Swiss mod in order to study different charging approaches. So we check what is the case without EVs and compare it with instant charging, which means that the car, it charges if it's connected to the grid without consideration of current power system conditions, and they are charged as fast as possible. Smart charging only happens if it's economically viable for the EVs to charge, which means when the electricity prices are low or the load is also low, or we have a lot of renewables in the system. Restricted charge smart is basically a delayed in the night hours for charging EVs. So instead of starting charging at 8 p.m., we allow only the EVs starting to charge from 10 p.m. on when the electricity prices are low, and to the end is the V2G, or vehicle to grid, which allows the vehicles to charge when it's more competitive, but also use them as a batteries if the total energy system needs this kind of electricity in the peak hours. Sorry. Okay. Regarding the capacities that we use, I just only want to show you that there is a withdrawal of nuclear, not only in Switzerland from 2030 into 2040, but also in the other countries. There is quite a reduction, and a small increase in gas as well. For Switzerland, we see that the demand doesn't change that much, but since the capacity of solar will increase quite a lot, we have our residual demand decreasing from 2030 to 2040, which means that this is the demand that will be satisfied by other technologies, not from renewables. Okay, for the EVs, so we model between, depending on the scenarios, we model between 0.1 to 1.8 vehicles, million vehicles, which represents around 2% of the total car fleet in 2030, up to 33% in 2040. Overall, the power consumption of these EVs is rather small compared to the overpower demand, represented to maximum 0.17% in the EU and 9% in Switzerland. Since it's quite demanding to model each individual vehicle, so 1.8 to 2040 in the model, we cluster the vehicles, so we aggregate them in order to group the cars that have the same driving pattern and the same car characteristics. So now let me dive into the results. So first, let's talk about the prices. Here you have two tables. The first one shows you the average prices in euros per megawatt hour for EU and Switzerland for the different charging systems, and compared to the case where we don't have EVs in the model. So as you can see, the Swiss EVs have a small effect on European prices here, around 2% in 2030 and 2.5% on 2040 on average. This is the change between the base case and the other scenarios. However, when we go to Switzerland, we see that electrical mobility has a considerable effect. In fact, if we compare each charging scenario to the EVs, on average, we have an increase of 60% in 2030 and 22% in 2040. We can also see that instant charging presents highest prices, and V2G or smart charge present the lowest ones in Switzerland. Now, the second table shows us the average charging costs in euros per megawatt. This means the average payment to the wholesale market for each megawatt used to charge the EVs. The same here, the instant or restricted smart charging leads to the highest charging costs because it charges mostly on peak hours, but the smart and the V2G generates lower charging costs that are lower than the average market prices. So choosing more effective charging schemes like smart or V2G promotes considerable system improvements by lowering market prices and providing profits to the electrical vehicles owners. Now, okay, so this picture here, I'm showing you what will be the seasonal effects, especially in the times where we have high demand, like in winter. So we have 4 pictures that compares each charging modes to the base case. So here on orange, we have our loads. The dash black line is basically the price in base case. The solid black line is the price of each scenario. We have the renewable generation representation in green. And finally, in orange, we have the demand from electrical mobility for each charging scenario. And we see that in periods of high loads, prices can reach levels up to 350 euros per megawatt hour in the no EV case, for example, but V2G that is represented here and smart charging here helps to smooth electricity prices and prevent load shedding by allocating consumption in the right nodes of the grid. See, like the prices have a smooth profile compared to the base case. Having instant charging demand when peak load occurs and generation is insufficient to satisfy demand increases prices when compared to the EV case up to around 800 euros per megawatt hour in the worst cases. And there is no big difference in the restrict smart charging. And finally, as you can see here, is the blue line is the generation from V2G, which means is the generation, so is the demand that is going to the grid again into the system, and basically it goes more when the prices are higher. You see here. Okay, so here in this picture, we want to represent the residual load duration curve in 2040. So this means is the load that will be satisfied by conventional technologies, not with renewables. We have here the residual demand of the no EV case and the dashed line, ordered on a decent way. These are the average prices, also ordered on a decent way, and finally the average demand for the different charging profiles. So we reported the average values over each 1/5 of the hours of the year to focus on the long-term trends rather than on short-term and noisy outcomes. So hours with similar characteristics are aggregated. So as the residual load decreases, as you can see here, the prices also decrease. So V2G provides the lowest prices at the peak hours. So you see here is this red line. Instant charging is at the highest level when residual load is at the peak. You see it here, this line here. So because the driving profile and the resulting consumption happen at the peak hours. Also V2G and smart charging concentrate its consumption at times where residual load and the resulting market prices are lowest. So it will be in this part of the graph where we have the V2G consumption and also the smart charging one. And restricted smart present a more constant profile, this blue line over the year. So what are then the implications regarding the change on dispatch between each of the charging approaches and the baseline case? So comparing these scenarios to the one where we don't have no EVs, we see that the introduction of electrical mobility under smart charging, that would be this light green, and V2G, the gray one, increases the use of hydropower plants, which have the lowest marginal cost compared to the thermal generation. So you see most of run-of-river and then and pump, they usually increase in 2040. Under instant charging, power generation from dams and run-of-rivers cannot be increased that much because the charging occurs in periods at the full capacity. And the effect of EVs charging behavior on dams and run-of-river power plants are marginal, since the annual generation profile mostly follows the annual hydro flows. Okay, so what happens now then is that the main changes now that you can see in both graphs are in the pump storage case.
Just for your information, Carla, you've used 17 minutes.
Okay, great. So this means that pump storage is used less in the smart or V2G charging cases considered because prices are low, which reduces their arbitrage opportunities. So, and storage use increases slightly under instant charge because of increasing arbitrage opportunities between peak and off-peak hours. So if we go now to the idle revenues, you can see this. So idle power plants benefit from the increase of electrical vehicles, because we can see that for the three technologies, idle revenues are higher for cases with EVs. Dams have the higher revenues compared to run-of-river, as they are more flexible to synchronize their production with peak hours prices, while instant charging provides the highest revenues. For example, V2G, on the other hand, presents the lowest one, since instant charging increases prices, so these technologies will benefit more under this scheme. For the pump storage, I already said that they benefit from arbitrage from storing electricity in periods where prices are lower and generating in peak load periods. And in fact, they represent the highest revenues, especially for the instant charging case. However, the introduction of electrical vehicles also increased the pumping costs, but the choice of charging scenarios has a little effect. Finally, let me just get you to the CO2 emissions. So without no surprise, the introduction of electrical mobility raised the CO2 emissions, but this increase is not considerable. Smart and V2G present the lowest CO2 emissions. And if we go here to show the average CO2 emissions per distance travel, we see that the increase on electrical mobility shows little effect on operational CO2 emissions. So for the worst case, 1.48 grams per kilometer in 2030 and 0.30 grams in the best case in 2040. So the electrification of transportation sector has a quite an effect on reducing the CO2 emissions per distance travel. So just to conclude,
you have to wrap up, Carla, if you want to let some room for questions.
So I just say that with no surprise, the CO2 emissions have been decreased. We see huge effects on arbitrage for the idle power plants, and the best charging scenarios will be the introduction of V2G and smart charging. So it's now up to the policymakers to create the incentives so that the consumers adopt the best charging mode by using charging tariffs or decentralized demand side management mechanisms. So thank you so much. And now I'm taking questions.
So thank you so much, Carla. There's a first question from Annie.
Okay, cannot.
Annie, maybe you can ask it.
Is there a behavioral impact or demand response in your model? It means reactions to price changes. So in Swiss model, no. So this is what I'm just presenting. We don't have the demand side response because we only are modeling the TSO way of managing the system. To include this, so we only get the demand or the electrical vehicle demand that is provided from the other agent model, from BEDM. I hope I have answered. So maybe we could include also for us the demand is quite inflexible. So.
Thank you so much. Other questions? All right. So then I think we've had a long and an intense session. Thank you all for the presenters for your presentations and for everyone else for their questions as well. Enjoy the rest of the conference, and would have been great to have you here in Paris with the great weather. For those of you that are not here, that's the current situation. But hopefully you get a chance to come to a Paris conference in the future. All right, so enjoy your meals wherever you are, and hope to see you soon at some point. Bye-bye.
Thank you, goodbye.
Thank you, bye.